Welcome to Lesson 4, Lewis diagrams for covalent compounds. Our lesson objectives: construct Lewis dot diagrams for covalent compounds containing single and multiple bonds and determine the number of electrons shared in a covalent bond. For a covalent bond to form, all atoms must have a full valence shell of electrons. And they're going to share these valence electrons either equally or unequally. For an atom to form a bond with another atom, they must share then a pair of electrons, a pair meaning 2. So we're going to look at our first example. We're going to look at the molecule of hydrogen. So before we actually construct our Lewis dot diagram for this covalent compound, recall that really the driving force for a chemical bond is the attraction for electrons from one atom to the electrons of another and vice versa. In a covalent bond, they end up sharing these electrons because they have similar electronegativities or similar attraction for electrons, and so no one really wins this game of tug of war like in an ionic bond. And so they end up sharing these electrons either equally or unequally. Okay, so how do we build our Lewis dot diagram? So first thing I want to do is I want to look up the number of valence electrons I have. So since there are 2 hydrogens, each one has 1 valence electron coming from the electron configuration here. So since I have 2 hydrogens, 1 plus 1 is 2. There's a total of 2 valence electrons that are going to occur between the 2 atoms of hydrogen in this molecule. So the first thing I do is going to draw my first H with its 1 valence electron, and then my next H with its 1 valence electron. And you'll see that they don't have a full valence shell. Now recall that hydrogen, for a full valence shell, it's not 8, it happens to be 2. It's one of the exceptions. They form a stable duet. And so how do they actually form a chemical bond? Well, this hydrogen atom is going to attract this electron, and this hydrogen atom attracts this electron. And they start pulling on the electrons, which pulls them in and forms a chemical bond. And they end up sharing their electrons to form a shared pair, which is a chemical bond, as you can see here. And now they both end up with a full valence shell of 2 electrons, again by sharing this pair. And we can replace this shared pair of electrons with a bond line, which we see here. So either one is correct for a Lewis dot diagram, either the shared pair or that bond line. Here's another visual. You can see it. Here's the first hydrogen on the left. It has its 1 valence electron, and here's the one on the right. And so this nucleus is going to attract this electron, and this nucleus attracts this electron, and they come together to share this pair of electrons, forming this covalent chemical bond. Let's see another example. This is another diatomic element. This is the molecule of bromine. So the first thing I want to do is look up the number of valence electrons in bromine. That's this number here, this last number in the configuration, which is 7. And since there's 2 bromines, I have a total of 14 electrons in my molecule. So what I'd like to do is draw one of my elements first and give out its 7 valence electrons. So give out 1 to each side until I run out. So 1, 2, 3, 4, 5, 6, and 7. So you can see it doesn't have 8, which is a full valence shell. And so where I have the single electron, that's where I'm going to form my chemical bond. And so I'll bring in my other bromine. Now this bromine also has 7 valence electrons. And what I like to do is I like to complete the bond first, this shared pair of electrons. So I'll put my first electron there, and now we've made a chemical bond. And then I'm going to give out the other 6 electrons to give myself 7 electrons for this bromine. So here's 1, 2, 3, 4, 5, 6, and 7. And so you can now see that they both have a total of 8 electrons. And they obtain that by sharing this pair of electrons. This is my covalent bond, my shared pair of electrons. And so I have 2, 4, 6, and then 8 by sharing for this atom of bromine, and the same thing for this one. And we can replace that shared pair, if you'd like, with a bond line. So again, either one is a correct Lewis dot diagram. We figured out there's a total of 14 valence electrons, so you can check to make sure that you didn't give out too many or not enough. So we have 2, 4, 6, 8, 10, 12, 14 electrons, and that's what I calculated out. Let's see another example. Let's look at the compound HBr. So first thing I want to do is look up the total number of valence electrons. So bromine has 7, hydrogen has 1 for a total of 8. Now whenever hydrogen's involved, I always start with the other element first because hydrogen can only have 1 bond to it. So I'm going to start with bromine first. I'm going to give it 7 valence electrons, so 1 to each side. 1, 2, 3, 4, now 5, 6, and 7. So I have a uncompleted valence shell here, so I'm going to form my bond, bring in my hydrogen. Now hydrogen has 1 valence electron, as we can see here, and so when it brings its 1 valence electron, they're going to share this pair here. So hydrogen is getting essentially 1 electron from bromine, and bromine's getting 1 from hydrogen, and it's not a transfer. They're going to share that pair. And now bromine has 8, which is a full valence shell, and hydrogen now has 2, which is a full valence shell. And again, I can replace the shared pair with a bond line if I'd like. And let's look at another example. This is water, H2O. So the total number of valence electrons, oxygen has 6, and I have 1 for each hydrogen for a total of 8 valence electrons. I'm going to start with oxygen first, my more electronegative element. I'm going to give out 6 valence electrons, 1, 2, 3, 4, 5, and 6. And so now I have 2 places I can form my bond. So I'm going to bring in 1 hydrogen and then the other. Each hydrogen brings along with it 1 valence electron. And so they end up sharing these pairs of electrons. So oxygen is getting an electron from hydrogen through this shared pair, as well as this hydrogen. So now this oxygen has 8 valence electrons, which is a full valence shell, and each hydrogen now has 2. We can check our total, 8 valence electrons, 2, 4, 6, 8. So we didn't give out too many or not enough. And again, if you want to replace the pair of electrons that are being shared, you can replace that with a bond line, which looks just like this. So either structure is correct. Let's check your understanding. Can you construct Lewis dot diagrams for covalent compounds containing single bonds? Now let's look at multiple bonds. So what happens when some atoms do not have a full valence shell of electrons when they're sharing just 1 pair? What they'll do is they'll share more than 1 pair. They'll form multiple bonds by sharing pairs of electrons. So we just learned about single bonds where we're sharing a pair or 2 total electrons, as in the case here for our molecule of hydrogen. But in some cases, like for oxygen, when we have diatomic oxygen, we can share 2 pairs or a total of 4 electrons. That's called a double bond. Or we could have a triple bond, as in the case for nitrogen, where we're sharing not 1, not 2, but 3 pairs of electrons, or a total of 6 electrons. So let's look at our first example, carbon dioxide, CO2. We're going to follow the same rules as before. So first thing, I want to figure out total number of valence electrons. So oxygen has 6, carbon has 4. Since I have 2 oxygens, I have 6 and 6 is 12, plus my 4 from carbon gives me a total of 16 electrons. Now, I like to start with the unique atom first, the one that appears only once. That's going to be my central atom. So that's the carbon. So we'll start with that one first. And then I'm going to dish out its 4 valence electrons, 1 to each side. And so really, I can form a bond on any side. I like to keep things in a straight line if I can, just easier visually. So I'm going to put my oxygens on either side. So I'll bring in the first one. Now oxygen has 6 valence electrons, so just as before, I'm going to give out the 6 valence electrons by first completing the bond. So we'll start here. So that's 1, then 2, 3, 4, 5, and 6. And now you can already see that this oxygen doesn't have a full valence shell of 8 electrons. But we'll come back to that in a second. So then bring the other oxygen in, and that's going to form a bond here. So that also has 6 valence electrons. So we're going to complete the bond first. 1, then 2, 3, 4, 5, and 6. And again, this one you can see also doesn't have a full valence shell. So oxygen, carbon, and oxygen all don't have a full valence shell. So what's going to happen is that we have these unpaired electrons here, and what they're going to do is they're actually going to pair up and move into the bonding site and actually form another shared pair of electrons. And the same thing for this unbonded pair. And so they move into the bonding site and share as well. So we create not just 1, but 2 shared pairs of electrons. And it looks just like this. So a shared pair here and a shared pair here, and we have another shared pair here as well as here. So 2 shared pairs is called a double bond, and we can replace these with bond lines if we'd like, and it looks something like this. Now notice that these unbonded electrons, it doesn't really matter where they go. Ultimately, they're going to move away from each other because they are the same charge. But in terms of drawing the dot diagrams, it doesn't matter if you leave them like this or you have them drawn like this. It does not matter. All right, let's look at another example. Let's look at a molecule of oxygen. And so I'm first going to look up the total number of valence electrons. We have 6 for each oxygen, so a total of 12. I'm going to write my O for my first oxygen, and I'm going to dish out its 6 valence electrons. 1, 2, 3, 4, 5, and 6. And so now I have 2 places it can bond. Again, I like to keep things pretty linear, so I'm going to put my oxygen right here. It's going to bring along with it 6 valence electrons as well. So first I'll complete the bond. 1, 2, 3, 4, 5, and 6. And so I have these unpaired electrons, and so they're going to come in and they're going to pair up in the bonding site and form another shared pair of electrons. And so when they pair up, we get 2 shared pairs of electrons, which creates a double bond. Which, if we wanted to replace these shared pairs with bond lines, it would look something like this. So again, either one is a correct Lewis dot diagram. And you'll see that the total number of electrons is 12. We have 2, 4, 6, 8, 10, 12. And each oxygen still has its full valence shell of 8. 2, 4, 6, and then 8, again, because it's sharing this pair here. And the same thing for this oxygen. Let's check your understanding. Can you construct Lewis dot diagrams for covalent compounds containing multiple bonds? And can you determine the number of electrons shared in a covalent bond? At this point, you should be able to construct Lewis dot diagrams for covalent compounds containing single and multiple bonds and determine the number of electrons shared in a covalent bond.